So we did the basic of all derivation, I think, and as I said, today we'll do some unique problems. Okay, so let's begin this problem. So as you can see, we have a semi-circular ring, and this is the base. This is the perpendicular bisector. So what is the value of ionite? Take the radiuses R. So the first question is, can you find the ionite? I think we have done this already, but still.
Yes, sir.
Yeah, without integration, just by common sense.
So first we know the I2 value, which is mr square, and then by perpendicular axis theorem we can find I1.
What is mr square?
Sir, it is I2 value.
I2 is mr square. Are you sure? What is the moment of inertia of a ring about its diameter? So see, what you can think like this. You can complete the ring mentally.
mr square by
Mr square by
2.
2. Correct. What you can do is you can complete the ring mentally, and then you can think this way. That what if the mass is of this ring is given m? This is also, so the total mass is how much? 2m now. So now what is the answer about I2? So I2, if you calculate, it will be mr square by 2. But for the ring of mass 2m, the answer becomes 2m r square by 2. But because we are only looking for the half of part, so we can say because of symmetricity that the contribution from the top and the bottom must be same. So the green color part will only contribute half of this value. Do you realize this? So first you make a complete circle and then think of what could be the answer. And it turns out to be the answer is same. Okay. So your answer is still mr square by 2. And in fact, I2 will be same mr square 2 and I1 will be also. Both are in the plane of the ring, and I1 I2 will be same answer mr square by 2. So now the question is, if I draw a line, maybe what do you think the I should be? What is the moment of inertia about this line?
mr square by 2.
Yes, mr square.
That's absolutely correct. It is mr square by 2 only. So how many of you are getting this answer?
So how?
There may be many logic, but you should get this answer. Okay.
Yes, sir.
So if I give you a new line, let's say something like this, you can think many ways. Like you can take this portion out of here, you can cut here, and you can put it here, back here, and it will not affect the answer. The reason is, with respect to the given axis, the mass is still distributed in the same fashion, whether you are putting up or down. And the moment you put this part here, it makes a semicircle, full semicircle. You can see this is semicircle, and this is a diameter, and therefore the answer is a mass over 2. The other way of thinking is, so we know that in a planar body, if you know the answer about two mutually perpendicular axes, then I we can write as I1 sin square theta plus I2 cos theta. And therefore, oh, luckily here I1 I2 are same. This is again a square by 2, we can take common. And this also proves that the answer is independent of angle theta you have taken. So even though it's a semicircle, but if you take the answer in the plane of the ring, the answer remains same. Okay. Okay. So then let's do the next question. So I hope you all remember the moment of inertia of a solid sphere. Correct.
Yes.
Sir, it was 2 by 5 mr square.
Correct. So now what we have here is this is the solid hemisphere. Now your question is, what is the moment of inertia about this axis? This axis is in the lying in the base of the hemisphere and passing through its center. Okay. So what should be the answer for this axis? What is I? Mass is given a, radius is R. You can take the radius as R, mass as M, and then what is the answer? So now you know the answer for the full sphere, correct? So the half will contribute half, right? Or in case if you want, you can complete it by symmetricity. So you know that if it is a full sphere, then what will be the answer? Then what we will
2
do
by
is
5 mr square.
correct. So you will just use the symmetricity argument and we'll get the answer. So if it is a full sphere, the answer is 2 by 5 m, or that is here 2m r square, and half will be 2 by 5 m r square. So the answer is still. Now this is not we are deriving. We are trying to use something called symmetricity argument. That if you can cut something into two equal halves, and if I ask the answer for the one of the half, then try to imagine that the other half is present, then what is the answer? And because of the symmetrical distribution of the mass around the axis, we can argue that the contribution will be equal from both these hemisphere, and therefore the answer will be this much. So this is how we exactly do it. Okay. So now this may not be the actual question. So the actual question is something more rigorous. So the question is, what is the moment of inertia about this axis, which is parallel to the given axis? Now this may be a challenging one. So let's say you know the I1 answer somehow by hook and crook, and now you're supposed to find the I2. Given that I2 is parallel to I1.
7 mr square by 5.
Hmm?
7 mr square by 5.
So I also got the same.
Think again, think again. It's not easy. Think again and think properly. Is I1 ICM? Are you sure? Is it passing through the center of mass of the body?
No, sir.
No, sir.
No. So if it is not passing through center of mass of the body, you cannot apply the parallel axis theorem, correct?
Yes, sir.
So you will do the, first of all, you will draw the axis which passes through the center of mass and parallel to the given axis, and you apply the parallel axis theorem between these two times. One for this NICM and then for this NICM, and eliminating that will give you I2. So can you do that? You got my point, what I'm saying?
Yes, sir.
So anybody getting the answer?
13 by 20 must be.
Okay, so where is the center mass?
3r by 8 from the base.
Correct. So 3r by 8 from the base, it is somewhere here. Let's say maybe here. So first of all, we need to draw this center of mass, and let's call this is IC. Now the theorem we apply for the ICM and I. So I can write I1 equals to ICM plus M 3r by 8 whole square. And for I2, what I can write is I2 equals to ICM plus M 5r by 8 whole square. You can subtract from R to get the other answer. And once you have these two answers, because you're looking for I2, and you can also get ICM also, because I1 is known to you. But right now we are interested only in I2, not in I1. So what we can do is you can subtract. So I can say I2 minus I1, the 2 minus 1, because I can say I2 is bigger, is equals to M R square by 8 square 5 square minus 3 square, which is how much? 16.
Yes.
So this is M R square by 4. And because you know the I1 value, so you can get I2 now. So I2 is how much now? So MR square by 4 plus 2 by 5 MR square. Okay, so 1 by 4, 2 by 5 is how much? So it is 5 plus 8, 13 by 20, right? So I2 is how much?
13 by 20.
Correct, no?
Yes, sir.
So now these kind of questions are like not very explicit. You need to think more deeply to understand that when we apply the parallel axis theorem, it is not between any two axes which are parallel. It is between the axis which is parallel to the ICM. So unless you don't realize this theorem, you will get the wrong answer. What you said is the very common mistake which I have found like among students. So they do this, they commit this mistake very often. Okay. So similarly, if I draw a disk, so they say this is a half disk. So you know the answer for the base. So now, first of all, how to begin with? Like first, you need to ask yourself that which answer I know or which answer I can find easily. So finding the base answer is easy because of the symmetricity argument. Now, what is symmetricity argument? If I complete this disk, then I can see the answer. So if you make it half, the answer will remain the same. So therefore, this answer, or you can also think that you can slice this disk into two equal pieces and then just unwrap it onto the other side, so it will make a complete disk of thickness half. So there are many ways of thinking. So now the question is obvious. what is the moment of inertia about this, about the tangent which is parallel to the base. So I'm looking for I2, and I know that we can get the answer I1 easily. Now this is not something we will mention to you, but now the question is, can we find I2 if I know I1? So find I1 and I2. So tell me the answer. So these two are parallel axes. You can do this. So anybody doing this question?
Yes, sir. So answer is mr square into 1 by 4 plus 3 pi plus 8 by 3 pi.
फिर से बोलो.
Mr square into 1 by 4 plus 3 pi plus 8 into 3 pi by 3 pi. So
3 pi
3
plus
pi
8
divided by 3 pi, not 8 pi, 3 pi. Half.
like this. Oh,
Yes, sir.
like this. Okay. So this is the value of I2, right?
Yes, I2.
And what is I1?
I1 is mr square by 4.
Correct. So for I2, it's pretty straightforward. So we know the center mass. If I say this is center mass, this is how much? 4 by 3 pi.
Yes, 4r by 3 pi.
This is r into 1 minus 4r by 3 pi. So we can say this is ICM. So I2 will be ICM plus m r square 1 minus 4 by 3 pi whole square. And I1 you can write as ICM plus m. So let's subtract. I2 minus I1 is how much? AMR square common. So 1 minus 4 by 3 pi whole square minus I2 minus I1 is MR square, and then you can expand minus 2AB. So I2 will be I'm getting a different answer. So you did the same.
Yes, I just, the subtraction part, I made a mistake. I made, actually, I did I1 minus I2.
No, no problem. So now I hope this is clear to all of you.
Yes, sir.
So now these kind of questions are of course not very common for the regular exams, but in JEE you can always expect.
So can I show the previous?
Now I will tell you like what kind of question you will expect in the examination.
No.
So the question that you will expect in the examination will be based on the relation only. So they will ask you that, let's say, now this could be for any examination, for medical also. So this is what they do. So now you can see there is a cone. It could be hollow, it could be solid, depending on. So I can mention it. And let's draw two parallel lines. So these lines are parallel to the, okay, parallel to each other and perpendicular to the line of symmetricity. So this angle is 90. Basically.
So solid cone.
You can take both cases. The height is h. So now if I say this is I1, this is I2. Now definitely you know which one is bigger, right? So which one is bigger, I1 or I2? I1, correct. So now the simple relation is find a relationship between I1 and I2. So there is no need to find the answer of I1 and I2. The relation between I1 and I2, that's it. Find I1 and I2 relation for A hollow cone, B solid cone. That's it. And this is not at all difficult. So this is the basic application of parallel axis theorem. So what you need to know is the value of center mass for each case. So for hollow cone, where is the center mass? From base.
by 3.
And for solid cone?
H by 4.
H by 4.
Has
Okay.
before.
So if you know this answer, then that is more than sufficient to get the relation. So go ahead and tell me the answer. Like you can say I1 equals to I2 plus something, or I2 equals to I1 minus something. So anything like that. So this is what you can expect in the examination. That they will not let you derive the formula of I1 I2 independently, but given I1 I2, you can find the relation. And this has been asked by the many examinations, including NEET also. So this is the simple application of parallel axis theorem.
Got it, sir. So I1 is equals to I2 plus
Hmm.
mh square by 3 for hollow, and for solid I1 is equals to I2 plus mh square by 2.
Plus by
mh square
2.
by 2. Oh, yes.
Is this answer? Anybody, I mean, anybody else getting the same answer? So center mass is, let's say, here. So okay, well, let me make it a general formula. Like you can say A, or maybe I can write x1, x2. So I1 we can write as so this looks nice to remember. You can always use this formula to get the answer. So I1 minus I2 will be x1 means distance from I1 to the center mass, which is okay. For the first case, it is 2h by 3. So 4 by 3 minus h by 1 by 3. So 4 by 9 minus 1 by 9. 1 by 3. Yeah. A is the right answer. And for B part, it is 3h by 4 minus h by 4. So 9 minus 1 is 8 upon 16 is 2. Okay, that is the right answer. So both answers are correct. Okay. So I hope this is not difficult. So you can always use this relation directly to relate the two parallel axes, because the center mass will come into picture. Okay. So look at this question now. So most of the earrings comes in the shape of hemisphere. Let's say the big earrings. Design this. Okay. And now we have the axis. This is hollow hemisphere. We have done this for the solid hemisphere. So what is the moment of inertia about this axis? Which is parallel to the base. Tell me.
Yes, sir.
So you can find the answer for the axis passing through the base, actually, the base, because the base axis is like symmetrical axis. If you complete this, full sphere, think about it.
So I1 is equals to I2.
Yeah, correct. It is ionic I2 for sure. So the base answer, this answer will be same because the center mass is exactly at r/2. So it is equidistant from both. So because it is symmetrically located from both sides, so the answer will be same as this answer. So if you know this answer, you know the answer of the top. And what is I1?
2 by 3 mRs.
Very good. So it is 2 by 3 m square. That's the right answer. Okay, so now this is nice. So we have done a lot of problems. So let's do this problem. So it's a square lamina of side length A. And now I'm doing the axis which is parallel in the, say, in the plane of the body, and something like this. And this angle is 15 degrees. So what is the moment of inertia about this axis lying in the plane of the lamina and making an angle 15 degree as shown in the figure? Okay, so do this question. Done? Okay, not done, of course. Did anyone try this question?
Yes, sir.
Okay.
Sir, M square by 3.
How much?
M square by 3.
No. Think again. It's not easy. Challenging.
So just 1 minute.
Take your time. Not easy. It's a challenging problem.
So 7 m square by 12.
No, not that. This is a real challenging problem. So again, so if you remember the last lecture, we can draw a line parallel to the given axis and passing through the center of mass. And what you remember that any axis which passes through the center of mass, that is the center of the square, this will have the answer, fixed answer. What is the answer?
M square by 12. So I was doing the same.
It
But
is
I
m
just
square.
want to calculate the distance.
Now the only question is what is the distance between the two axes? Now distance is the challenging part. That is the mathematical thing. So you can join the center to this because we know this length. And what we are looking for is this length, the perpendicular, something like this, correct? Or better you can draw something here. So it's up to you to get the answer. So to get the answer, what you need to know is the angle. So this is 15 degree, this is 45 degrees, correct? So we all know this is 15, this is 45. So you know this answer. This angle is how much? This is 30 degrees. I hope you got the answer now. Now this is easy. So because this is 30 degree and this length we know because this is the half of the diagonal. So this is a by root 2, right?
11 by 12 well,
11 by 24, I think.
11 by
So
24.
the yeah, so the perpendicular distance is a by root 2 cos 30, which is root 3 by 2. And now you can write the answer is I equals to ICM plus M d square. And d is how much? 3a square by 8. So the I value is 11 by 24. So now, of course, this is something not very easy. So finding the distance between the two parallel lines was a geometrical task, and indeed it was difficult. Anyway, so let's do something basic questions like this. Let's say we have two rods of length L each and mass M each. And we want to find the moment of inertia about an axis passing through this hinge and perpendicular to the plane. What is this I? Now, no matter what is this angle, answer will be same. So you can see this. There are two rods. You can just find the answer for each rod separately and add the value. So the axis which I have drawn, which is like normal to the plane, is end of both the rods, and we know the answer for end, right, directly. Or you can do it the parallel axis around. So center mass of each rod is L by 2 away, as you can see. So I we can write as ml square by 12 ICM plus ml by 2 whole square, and the repetition is 2 times. Just to make it 2 times, and you get the answer. So I is how much now? 2 ml square by 3. So I think this is pretty straightforward. So
So can you explain again that?
just apply the parallel axis theorem for each rod separately. And the hinge is what? Hinge is normal to the plane, as I said. Okay. Sorry, the axis is normal to the plane. Okay. So I hope you understand the meaning normal to the plane. Yeah?
Okay, understood.
Okay. So anyway, do this problem. So let's say this is some sort of modern earring. Let me design this. So these are the sides of a square, but one side is missing intentionally. Because as I said, this is a modern instrument earring. Something extraordinary should be there. And you can think the axis of the rotation as the axis which is perpendicular to the plane. Assume each side has a rod of length L, mass M each. And these are right angles. So what is the moment of inertia I? Find I. Tell me the answer. Okay, so what's the answer?
Three ml square.
So you have to apply the parallel axis theorem for each rod separately, right?
Sir,
Because
yes,
you know the answer for the center mass, and the answer is ml square 12. So because it is ml square 12, if I name it rod number 1, rod number 2, rod number 3. So for I, how to write I? I is for 1, 2, and 3. So moment of inertia of the first rod will be how much? ml square by 12 plus m L
L
by
by
2 whole,
2.
which is ml square by 3 basically. You can also remember, but just in case if you want to write. And the next is the next rod center mass is not at a distance L by 2. It is something like this. So we need to calculate this length. This length is how much?
5 square. Under root under 5 square.
So root 5 L by 4, huh? 2.
Sir, 2.
So now this answer will become ml square by 12 plus m root 5 L by
2.
whole.
2
And
times.
the other rod is same, exactly same. It is also the same. So it's 2 times. We'll just do it 2 times. So we got the answer. How much?
3 ml square.
Okay, is it CM square? Yeah.
Sir, I mean, I got the same equation.
So m square by 3 plus, let me just check, maybe correct. And this is 5 ml square by 4 into 2, which is kind of 6, and 2, which is 6 only. LCM is 6, 1 plus 3, 15. 15, no? 16 by 6. How much is that? 8 by 3. Yeah, correct. 8 by 3 plus 1 by 3. Correct. This is the right answer. Okay. So now so if you create a so again this is a square lamina. Let's put something for decoration. This looks like some expensive earring. Okay. So this is a square lamina. All these are designing. You can ignore the designs. Square lamina of side length. So now you have to find the moment of inertia about an axis which is perpendicular to the plane and passing through the one of the corners like this. So what is the moment of inertia? You see, easy. You could do this.
So can you then explain the question?
This is a square lamina, that's it, of side length L, A and mass.
What is the circle?
No, circle is sub-designing. Just ignore the decoration. You may make a small groove like this. No? Okay. So you have no aesthetic sense about things. Okay, leave it. Think this is a square lamina of side length A, mass M. So what is the moment of inertia about an axis passing through the corner and perpendicular to the plane? That's it. Tell me now.
Will be 2 by 3 m e square.
Maybe. From the center we know this is a ms square by 6, right?
Yes.
Sir, 2 by 3 ml square.
ms square by 6 plus m a by root 2 whole square, correct? This is
Whole
what you
square.
did?
Yes. Yes.
Yeah, then the answer must be correct.
This is 2 by 3 m.
2 by 3.
Correct, 2 by 3 is. Okay, so let's do something more. Hmm. So the next is moment of inertia of truncated bodies. So the simple thing is you remove a part of a body. So what we do is we calculate the moment of inertia of the whole body and the body which we want to remove separately, and we subtract because it is a scalar quantity. So let's do this by some example. So again, we'll take the same earring example. So let me create a nice earring. I hope this looks like a earring. Okay. Now, if you look geometrically from a bigger disk, a small disk is removed. That's the only idea. And this radius of the smaller disk is r by 2. So definitely the r is the radius of the bigger disk. And it is also removed strategically from the close to the perimeter, so that the other end touches the center of the bigger disk. You can see here. And now you are supposed to find the moment of inertia about this axis, which means passing through the center and normal to the plane. So this is how also this oscillates. So now if someone is wearing this kind of a earring, it oscillates like this in a plane. So this could be a question of a simple harmonic motion. Find the time period of oscillation. So that is also what we'll do in chapter of SHM. But right now our only interest is to find the moment of inertia I. So you can take let
So
me
can you
phrase
show?
let from a disk of mass m and radius r, a smaller so let from a disk of mass m and radius r, a smaller disk of radius r by 2 is removed as shown in figure. Calculate I of remaining disk. Calculate I of the remaining disk about a given axis. Okay.
3 mr square by 4.
So how to do this question? So you can first do the big disk, and then your job is to find the moment of inertia about this axis. Then you draw the small disk which you are removing actually, and find the moment of inertia about the same axis. The axis must be same, and then you subtract. If this gives you I1, if this gives you I2, then I will be equals to I1 minus I2 because that is we are removing actually. So the M is given for this much. This is M given, not left side. The full disk is M. So now what is the mass of this disk? See, because the area wise you can see it's M by 4. So this is the easier way of writing the mass, or you could have gone into writing in terms of sigma and all. So that is also possible. And now you have to find I1, I2 separately because you know the mass, you know the radius, you can solve this. Now it looks like very much same. Like for both the disk, the formula will have similar pattern. Only R will be replaced by R by 2, M will be replaced by M by 4. So just you need to substitute the value and you get the answer. So now try this question. Once done, let me know.
So 75 by 64 hours.
Need to check actually. No, that is not the right answer, I think. Hopefully. So I1 is how much? It's mi square by 2 plus mi square, which is 3 by 2 mi square. So that's the easy answer. Minus 3 by 2. The m is replaced by m by 4 and r by 2. That's it. That's it. Answer. So if you have done the same, you'll get the same answer. How much is that?
Sir,
3 by
9 mr square by 8.
maybe 2, 3 m square by 2 into common 1 minus. It's
And
15
it is
by
45 by 48 hours.
correct. You can add divide by 3, no?
Yes.
You can divide by 3. No? 15 by 16 to 3 by 2. No, what you say? 15, but 32. This is 50. It's not 48. It's 32. I think. 15 by 16 to 3 by 2 means 15 by 16 to 3 by 2. It's 45 by 32. I'm asking. 45 by 32. This is what you got. All right. Now imagine if I switch the answer. Let's say if I say that m is the mass of this object, then what is the mass of this object now? If I relate m this way, if I call this is the m, then what is this m? This will become m dash. This will become m double dash. So can you find m dash and m double dash if you know m? So then to write in that way, you write sigma into area. Sigma into area. And now sigma, what is this sigma? It is m upon the total area, which is pi r square minus pi r square by 4. This is how I have to think. So what is given is very important. So if they mention m is the mass of the remaining disk, then to get the other mass, we have to do this calculation. So this turns out to be how much? 4 by 3. So of course the pi square into sigma will become 4 by 3m. So this becomes 4m by 3, and this becomes how much? M by 3. Correct. So this is how we have to convert the mass. If that is given, then how to write? If this is given, then how to write? So the question that we began with, it gave that the m is the mass of the full disk from which we have removed the other disk. So let from a disk of mass m and radius r, a smaller disk is removed. Now this question can be rephrased in other way also. Okay. This could be rephrased into other way also. So you have to be very careful that how it is rephrased and then how we can convert. So the best way to proceed is calculate the mass as a sigma into area, and sigma you express as per what is given. So this is the challenging part, and this is a very old JE problem actually. I hope you all have seen this problem somewhere. So yeah, next one. Same question with a twist. So you know this answer is r by 2. And you got the answer for this axis, right? Now, what if I draw one more axis here? And now I'm naming it. So I'm calling this as I1, this side. So you just got the answer. I think you got I1. So now my question is different. So what is the answer? Like, what is ion might? I want this ratio now. Same question.
So,
Yes. Tell me.
sir, I got I2 18 m1 square by 16.
How much?
Sir, no, sir, I had doubt in the last question. Sir, that's why.
Yeah, tell me your doubt.
Sir, I'm not getting that equation after that negative sign. 3 by 2 m by 4 into r by 2.
So mass of the disk is how much? M by 4. And how to get the mass? Area proportional.
Yeah.
So what is the area of this disk? 1/4 of the original. Correct.
Yes.
Then what is your doubt? So So what is the moment of inertia about axis like this, normal to the plane? M square by 2,
Yes.
and then add the r value, parallel axis curve. So what is the answer now? 3 by 2 m square, correct? For this part, actually we are writing for this part.
Hmm.
So I1
So
is how much?
I'm not getting for the small distance.
So you can just do the same thing, na? Apply the same concept here. So what is the moment of inertia about this line?
M by
M
4
by
into R
4,
square by 4.
m by 4, r square by 4 by 2.
Yes.
M r square by 2. What is the problem?
Okay.
Plus m r square, parallel axis theorem. That's it.
Yes, sir.
No, no problem. So now I1 we know. So the now next question is what is I2 now? For I2, it is easy because for bigger disk, whether you find about I1 or I2, it's the same answer. But for a smaller disk, the distance will change. This is the distance of a smaller disk from this I2.
5 by 4.
Yeah. This is R and this is R by 2. This will be how much? Root 5 R by 2.
2.
And therefore, the I2 part will be 3 by 2 mr squared minus, that is same. And now this will be m r square by 2 plus m r square. So I2 turns out to be how much? Minus mr square upon 4, 4, 16, 5 by 4, 5 by 16 into it's 11 by 32. So this is 96 minus 22. No, not like this. I should have done easily. 32, this is 16, 3, 48 minus 11. 37 upon 32. So now I1 was how much? What was I1? 45 by 32, right? Oh. No, this is fine. Hmm. So now what is I1 by 2? I think this one, 45 by 37. Yes. Okay. So this is the question that you will also come across in this is again J advanced form only. I don't remember the exact value, but this is something, yeah. So now we'll go to the last concept that is called the radius of gyration. And the symbol for the radius of gyration is K. So what is the radius of gyration? It says that if you have some random object, And if you try to find the moment of inertia about any given axis, so definitely this will give you some answer. So let's say the moment of inertia of this body about this arbitrary axis is I. Now the radius of gyration tells you the answer that what if I want to replace or substitute this entire mass as a point mass, then what separation will give me the same answer as the answer I got earlier? So now this is the K value. So K is the separation at which if you keep the point mass m, which is same as the mass of the body, then the moment of inertia that it will offer is same as the body was offering earlier. So the idea is simple, the I must be equals to mk square, and therefore the K is actual I upon m under root. So that is how we find the radius of gyration. What is the significance of this? So again, the significance is the K is smaller, the simple the moment of inertia is smaller, or the mass is closer to the axis. Okay. So let's do it for some common bodies, and in fact, you should remember this. So if I give you a ring, and this is the axis, and the radius is r. We know this radius is r. I hope you know the answer. What is I? I equals to
MR square.
m r. Now the question is, if I want to replace this by a point mass, then at what distance I must keep? So I must keep at distance k. So the answer will be mk square. So now if you compare, the k turns out to be r only, right?
Yes, sir.
It means that it means the entire ring can be replaced by a point mass at a distance r, and that is what we have done in the very beginning. So similarly, let's do it for the disk. So for a disk with the same axis, so we know the I answer is how much?
MR square
By 2. And now I want to keep at a fixed distance k as a point mass. So this must be mk square. So now if you compare, the k turns out to be r by.
R by root 2.
So for, okay, again let me just write it for uh, hollow sphere, the standard one, the hollow sphere about this axis. If it is a hollow sphere, then 2
By
by
7.
3 m square, and this one we must equate with mk square. So now k is how much? And so for a solid sphere, and of course it's a similar thing. I'm not going to make it something extra.
R root 2 by.
Correct. So it is the equivalent distance actually, which you can replace as a point mass, which will offer you the same moment of inertia as the body was offering. So that is the idea of radius of gyration. So now you may get question like this also. So let's say we have an axis and we have 3 disks. One, let me make it closer. Two. So all are identical disks of radius r. So the radiuses are, and the disks are touching this axis like this. So question is, if the mass of each disk is m, what is the k value for the entire system? These are disks. Could be sphere also. And so let's begin with disk first.
So is it root 3r?
But
Root 3r.
okay. Anybody else getting some similar answer? So first of all, you need to find the I actually. So this is again the question of finding I. So what is I value first of all? I will be for the green disk, it's m square by 4 because it's a diameter. But what about the blue and the or I mean yellow disk? It is m square by 4 plus m square 2 times. And this entire value should be equal to how much? The total mass of system, like a point mass into k square. This turns out to how much? M square by 4. This is 5 by 4 is 5 by. So when you have to replace by a system, the system mass should be kept not to only m. You have got 3m. So that is the system mass. So it's 11 by 4, no? This is also this check, right? It is clear. Now, if I give you the same question, and if I tell you, okay, this is not a disk, it's a solid sphere, the answer will be how much? Tell me the answer.
So 4 by root 5. Hello?
Sir, I am getting 4r by root 15.
How much?
4r by root 15.
So I'm getting 4r by root 5.
Okay.
Sir, 4r by root 15.
So 15. Okay.
No, I'm also in root 15, sorry, not 5. Root 15.
So I think it's 2 by 5 mi square plus 2 by 5 mi square plus mi square into 2 is 3m k square, right? This is what you did.
Yes.
So this is 714 by 5, 16 by 5, 16 by 15. So 4
Yes.
by root 15. Yeah, that's correct. This is the right answer. So phase. So of course there is no end to the problem. So what I'll do, I'll do just one or two more problem, then I'll wrap up this chapter. Not this topic. So let me do this question. So in the recent examination of JI mains, assume all are symmetrical, although it doesn't look, but accept it. So each will have these are spheres, solid spheres of mass n. It's more simple. And okay, now this is the case. I am looking for the moment of inertia about this point. Okay, this point here. What is I about this point, and what is the radius of gyration and k? So this will solve. Actually, you will solve two questions. First, you find the I about this axis. This axis is passing through the center of the sphere as shown, and normal to the plane which I am drawing. Okay, so you can try this question. Take radius as r. No? Each radius is r. Oh, maybe just the point P we will take here at the this coordinate. Find this side and find I also and find k also about this axis. So find I and k. Okay, so try this out.
So each radius is half. No?
Yes.
So can you please do this thing?
How much is the answer?
I didn't get it. Can you please show?
See, it's difficult to get the IP. So first, what you need to do is get the answer of this open about the center IO. Finding IO is easy. Why? Because this IO also happens to be the center mass of the system. So in a way, this is ICM. And because it is a sphere, so we can say 2 by 5 mr square for the central sphere. But for remaining, it is 2 by 5 mr square plus.
So it's R root under 369 upon 5.
You can check this out, right? This is ICM. 2 by 5 mr square plus the distance of the center of each sphere to the center mass. And this is 2R. Okay. So now you got ICM. And because this is ICM, so finding IP is not difficult. So for IP, what we can do is we can apply the parallel axis theorem, which is ICM plus 7m into 3R whole square. This is the answer. So how much is ICM by the way? So 7 times 2 by 5.
So can you again explain the first one?
Yes. Yeah. Which one? This one.
So how solving so
So what is the what is the moment of inertia of the central sphere about this axis, which is the normal to the plane when like passing through the diameter?
2 by
So,
5 mass.
correct. So for any other sphere, let's this sphere, this sphere. How to write the answer for this sphere about center mass? So the sphere answer is this much, yeah, plus m into distance of the sphere from the center mass, which is 2r. And this is same for all the 6 spheres surrounding it, right?
Yeah.
So we got ICM, and what we are looking for is IP. So we can apply the parallel axis theorem for the system. So now normally what happens, we normally apply for only one object. But the parallel axis theorem we can apply for any system of mass if you know the central mass. So you have to also learn this concept that ISM is not only about one particle, it is about a system also. And once you know the central mass of the system, you can apply, then get the answer. Okay. So yeah, so we got IP. And now IP we can attach this entire thing equals to 7mk square. The rest is up to you. This is the JE problem of I think 2018 or 18. Yeah, before Corona. Yes. So with this question, okay, we'll not end up. Now we have to do one more very crucial problem. And this is going to be challenging for you guys.
So can you show the last? One?
I think this will be the second last problem. So moment of inertia. Now this is very crucial because this is asked in all exams. of a cylinder. Now we know the answer for cylinder about the axis passing through the center of the base and the, something like that. Now we have a cylinder like this. Okay. So earlier we were finding the moment of inertia about this axis. Huh? We can remove this central axis like this. But the question has changed. So this cylinder is having radius r and length L. It's a solid cylinder. Now we are supposed to find the moment of inertia about this axis, which is passing through the center mass definitely perpendicular to the length. Okay, so this is the question. Now this is quite a different question. And we haven't done any question like this before. Okay. So what we can do now? We will definitely move x and cut dx as a regular job. What we are supposed to do. So now you can see that I have cut a small portion, and this small portion is like a disc, correct? And you want to find the answer about this given axis, which is difficult, but we can draw one axis which is parallel to the given axis and passing through the center mass of the disc that we have considered. Something like this. So now this line, you can say DICM because this is center mass of the thin disk which we have considered, and I want to find the answer about this axis. So I can say, let's say this contribute about this axis by value di, and luckily we can write the parallel axis theorem between the DICM and DI. So what is DI? It is DICM plus DM into, and if I call the distance at which we have cut x,
X.
x, and now it is only a matter of integration. So what is DICM? If you remember, so DICM is the moment of inertia of a disk about the diameter, which is answer is dm, radius is r by 4. you remember the answer. So now the first term is very easy to integrate. The reason is it's just m dm integration. So r being constant for the entire cylinder, we can just add dm. And for the second case, we're gonna dm equals to mass per unit length into dx. Now, this is how you can do minus L by 2 to L by 2. This is like just like a formula for rod. So this becomes the formula for disk about diameter plus rod about the center, which is m square by 12. This is the combined answer of the system. So this question is very famous.
Sir, but why do you take DN or DI?
Pardon?
So why do you take DI?
So if I take a small part of the whole body, then should we say this is going to contribute everything or contribute a part in its own part? The eye I'm looking for, but what is the contribution of this disk to the eye? Only di, correct?
Yes, sir.
The eye is the moment of connection of the entire cylinder as whole. Na? So what you will contribute as a independent piece of or slice of the cylinder. So now this is very important again for the JE main point of view, NEET also, and so up to here you have to study. But I'll give you one more question where you can apply the same concept, but the radius will be variable. So that question is this. You can take a kulfi. So let's say find the moment of inertia about this axis. I, R, H, or maybe capital H. Yeah. So let's say this is solid cone. So same philosophy, and hopefully you can do it. So anybody who is interested in doing the calculation, else I will do this in no time.
Yes, sir.
Want to try? You can try for 2-3 minutes, and then tell me the answer. The only difference between the previous and this question is here the radius of the disk which you will cut as a slice will vary. And the limit of integration will be from 0 to h. Earlier it was minus L by 2 to plus L by 2. So these are the two differences between the previous and this question. But if you solve this, you know how to do this at least. Practice everyone.
Is it 3 by 5 mh square?
Yeah, tell me how much? How much?
3 by 5 mh square.
Bus. Anything else? So if you cut a disc, if you take a small piece of it, what you get is a disc. That's dx. And again, you have to do the same thing for the disc. Huh? It's the disc basically. The same thing is d. So you can write di equals to the elementary contribution about the given axis dicm plus dm x square. Now here the radius, you can take this radius as smaller. The distance is x, so you can say r by x is same as capital R by h. The r we can write in terms of x like this unitary method, and dicm will be dm r square by 4 because r is variable here. This part is easy, I think. Not easy. So di equals to dm. Dm will be okay. Rho into volume. So density into volume, which is pi r square dx dm into r square by 4 plus dm into x square. Now you have to substitute everything and then do the integration, which is indeed a tedious task. R power 4. So we can just write dr equals to r by h dx. That's a better way. So dx I can replace by h by r dr. Now this is easy for me because the r power 4 I want to keep, and dx I can replace by h by r dr. Now this is easy in terms of integration. And in the right hand side we have x square and r square, so we can do anything. So let's substitute r there, which is that is easy. So r square is how much? So very long integration, tiresome. Okay. And what is rho? Density is how much? M upon 1 by 3 pi r square h. So we can take a rho common. Pi h by 20 r power 4. Yes. Pi r square by pi h cube. And pi r square h you can cancel. Pi r square h. That's it. So I equals to 3m by 20 r square plus 3m by 5 h square. Oh my god, this is something big answer. Okay, anyway. So you can just practice for the sake of practice. That's it. And learn integration as much as possible. Learn elementary methods applying in different circumstances. So this will make you really very strong in physics, very strong. You can do any problem in J advanced because you know how to derive things from scratch. So that is a skill which you need to develop. And now I'm finishing this topic of moment of inertia. So we are done now. So now we are done with the moment of inertia. So what is next? So the next concept that we are going to learn is the kinematics. Yeah, that is better way. Or now the next topic is rotational kinematics. So I hope you have revised the chapter of circular motion. So
Yes.
anyone who has revised this chapter, circular motion, and if you have revised that chapter, then you must remember something like omega.
Yes.
Okay. So in rotational kinematics, we will study about the types of motion. See, a particle can move in only two ways. So a particle performs only two types of motion. Either a particle can move in a straight line or in a curved line. So when a particle moves in a straight line, we say rectilinear. And when a particle moves in a curved line, we say curvilinear. So in case of body, we have infinite particles. So when I say a body is performing a rectilinear motion, it means every point on the body is traveling the same direction with the same velocity, and hence every point of the body suffers equal displacement in equal time interval, however be small be the time interval. So the idea is if you have a body and if this body is taken from one place to other place in such a way that every point travels parallel to itself. So this point, if we choose some random point, this point will travel here, but this point will travel here. So no matter which point you choose, all will suffer equal displacement. No, I'm saying displacement is vector quantity, right? So when we say a body is traveling rectilinearly, which means every point on the body are moving in a parallel path and they travel equal displacement in equal time interval, however small be the time interval. That's the core idea. And now you can see that because every point is suffering equal displacement, equal time interval, so they must have equal velocity, equal acceleration, and so on. And therefore, to study the rectilinear motion, we must replace the body by one single point object, and generally we consider the center mass. So for rectilinear motion of body, replace body by point mass. Okay. Generally by its center. So this is what we do. So if you want to analyze the rectilinear motion of a body, there is no need to consider a body, just consider a part. So the next is what is curvilinear of a body. If you have a body, so now when I say curvilinear, every point will travel on a curve path. But this curve path will be parallel to each other, so they will never intersect. So in a curvilinear path, the body will not tilt. It will remain in the same orientation, but it will just travel in a way such that each particle will travel in a parallel path. But this parallel path will be curved instead of flat or straight. So this is called curvilinear motion. And because again the body is because not turning at all, the body is just shifting from one place to the place following a curvy path. Therefore, the motion of such body we can replace the body by center mass. So to analyze the motion when the body is moving in a curvilinear path, replace the body by point mass and then take the point mass as center mass. That is the process of analyzing the body. Now, for example, so I don't know if you can see that. Even look at this frame. This frame you can see. So this frame I can move like this. So you can see in this entire motion. I hope you can also see. Is the frame rotating? Can you see?
No,
Can we say this as rotation?
no, sir.
No, this is not called rotation. This is called curvilinear motion. And if I move this way, this is rectilinear. So rectilinear, curvilinear, rectilinear, like you can do like this. So this is like, so there's a difference between the rectilinear and curvilinear. In rectilinear, curvilinear, the paths are parallel, but one is straight, another is curved. So far, whatever we have discussed is together called translatory motion. So now these two we can capture under the category of translatory motion. So you can think this. The first category is called translatory motion. And under the category of translatory motion, we have rectilinear and curvilinear. But rectilinear and curvilinear are the examples of pure translatory motion, because here we prevent the rotation totally. So if we talk about the pure translatory motion, then we use the word rectilinear and curvilinear. But if I only use the word translatory motion, then it means it may have some sort of rotation possible, but it also have the translation for sure. So when I say just translatory motion, then I'm not affirmatively saying that rotation is happening or not. Translatory motion means rotation may or may not occur. I don't know. But when I say pure translatory motion, it means there is no question of rotation. It's pure translation, and then only we can define the rectilinear and curvilinear. So pure translatory motion will have two branches, rectilinear and curvilinear. But if I say translatory motion, then you can write like this. It may or may not, it may or may not be rotated. Okay. So now the translation is simple. Like when we say a body is translating, so what is the condition for translation?
There must be
Pardon?
so omega.
Pardon?
So omega must be
No, no, I'm saying condition for translation. When a body is said to be translating. So how you can say that, okay, no, this body is translating or this is not translating? How to differentiate? So let's say look at your fan. If you have a ceiling fan at your home, you can see the fan, and can you tell me that is your fan translating, yes or no?
Yes, sir.
Is it translating?
no, no. So
So
fans
why are,
blade,
yeah. So fan as a whole is a system, and you are saying it's not translating. So why, like, what metric you said this? Like, what did you see and you said, okay, no, this is not translating. So which kind of observation forced you to say this answer? It's not translating. And if you realize it is center of mass is non-moving, you can see.
Yes, sir.
So a body is said to be translating only when its center mass is moving or is suffering displacement with time. The condition for translation is body's center of mass must change its position with respect to time. That's it. So if it is happening, you can say translating, else you will say no, it's not translating. Okay. So translation in a ground frame is the absolute observation. Only by looking at the center of mass we can say whether the body is translating or not. So your fan center mass is not in motion, therefore we end up saying there is no translation, but it's a rotation. So now translation is easy to define, but what about the rotation? It is not easy. So rotation having a problem. So a body's rotation cannot be defined absolutely. So a body's rotation is only defined with respect to an axis. Okay. And there is no absolute definition. The way we define the translation, similarly, I cannot define rotation. That's a problem. And you need to understand this problem that rotation is meaningless unless you do not mention about which axis. So once you mention that rotation about this axis, then I can say something about it. Okay. So rotation is only meaningful when the axis is mentioned, else there is no absolute definition of rotation. So what I can say about rotation, it is only defined with respect to an axis. Okay. So similar to pure translatory motion, can we have pure rotatory motion?
Yes, sir.
So again, the answer is in the ground frame, no, but it could be in some axis. It could be about some axis. So because rotation is only defined with respect to some axis, so pure rotation is also defined with respect to some axis. So we need to search for such axis about which I can say the body is performing pure rotation. Okay. So let me try to explain this because this is a very difficult concept. Pure rotatory motion. So when a body is said to be performing pure rotatory motion, so I'll give you just some example. I don't want to make it this chapter
Second, to the last.
full of definition. I just want to keep it light. It should be easy on your mind. Rest I will share the notes. You can read the theory. I have written a lot of theory in the past, but now I'm bored actually writing the same theory again. So let's start on saying the meaning of or concept of pure rotation. So imagine this is a box. Just look into this. And this box after some time, or let me draw some axis also. So I choose one axis here, which is normal to the plane. And then what I do is I attach this axis to certain random point of the body. So I choose some random point. This is some imaginary axis. So it's not a physical object connected here. Just some thought. So let's call the name of this point which I'm connecting here is A, B, and C. So after some time, the box goes something like this. So the point A has come here, A dash. B has come here B dash and C has come here C dash. So what I do next is I again join the point with the same axis. And then I can check the angle. So you can see the A has gone to A dash, the B has gone to B dash, and this line has gone to C dash. So this may make some alpha, this is maybe beta. So alpha, beta, gamma need not to be same. It could be different. It could be same. I mean, I don't know. So this is the axis. So a body is said to be performing pure rotation about a given axis. And the idea is simple. If you look at any random point of the body and if you feel that all those random points have suffered equal angular displacement, then only you can say it's pure rotation, isn't it?
Yes.
So the common sense is that alpha, beta, gamma should not be different. Now look at the fan, the same example. So when you switch on the fan, you can see that the blades turn, every blade will turn by equal angle. And if it is not the case, then the blade will come closer or will go farther and eventually they will collapse. But because the angle between the blade is maintained because every blade suffered equal displacement. So if the first blade will travel by theta, the second will travel by theta, and the third will travel by theta, and so the relative angle remains the same. It's not changing. So this is the example of pure rotation. So your fan blades, or you can say fan as a whole, is performing pure rotation about the axis which is passing through the suspension. You can think that way, or normal to the plane of rotation. So that is the axis about which the fan is performing pure rotation. So pure rotation only refers to the condition that the given axis, when you observe things from that axis, you look at any random point and you feel that every point has suffered equal angular displacement in equal time interval, however small be the time interval, no matter what time interval you choose. So that is idea. So this is the case of pure rotation about given axis. So now this is something we can go deeper and try to understand it. Imagine if I draw some random shape body. Imagine this is a random shape body. Any body, you can just think of it.
So
And yes,
alpha is equal to beta is equal to gamma is equal to constant at any point like this.
no. Alpha, beta is not. How much fan blade will travel, I don't know, but whatever they will travel, they must be same.
Okay. Ah,
Understood? So let them travel how much they want. So whatever they travel, that must be same. Then only the relative portion will look similar. No? Okay. So now in case of this box example, the axis was somewhere away from the box, correct? So now I'm taking some random object. No, this looks nice. Eh? So now this is the random object. Sometime I can be artistic. So let's say this is the O point. This is some mask of flat paper. About O, let's say you're sitting at O, you're just some axis is passing through O. And if the axis is passing through O, no matter which point you choose on the body, for from the definition of a rigid body, we know that this point with respect to this point, or this point with respect to this point, or this point with respect to this point, all will remain at same angle, right? So this angle will change, yes or no? Will it change? Will it change ever?
No.
Definitely not. So if I rotate this about this axis, then every point will have fixed relative position. Correct? If A will travel by theta, then B has to travel by theta and C has to travel by theta. Then only their angle or their relative angular position will be same, correct? And that is the property of a rigid body. Now, what does it mean? Try to understand what does it mean. It means any point on a body, or you can say that if we have an axis which passes through the body itself, which is the part of the body. So any axis which is part of the body, if you observe the motion of the body from that axis, it is bound to be pure rotation. Do you realize this?
Yes.
So we have an axis, and the axis is part of the body. It is passing through the body. So if you observe anything from that axis, which is the part of the body itself, then the motion is bound to be pure rotation. Only when the axis is away from the body, then there is the problem. It could be, it cannot be. It can be, it cannot be. Both possibilities are there. So the thumb rule says that if the axis is part of the body, then the motion observed from that axis is bound to be pure rotation. But if the axis is not part of the body, then the body may perform pure rotation or may not perform pure rotation. So there are two possibilities which you need to remember. I hope this is clear. So for pure rotation, how to think? If the axis is part of the body, then the only rotatory motion will be pure rotation. If axis is not part of the body, then that axis or about that axis, the body may or may not be performing the pure rotation. So now the pure rotation becomes dependent quantity. It could be or it cannot be. So we will not be sure about it. But in nature, something very interesting happens. I mean, that's very, very powerful. In nature, even beyond the body, there is a possibility that you may get one particular axis about which the body performs a pure rotation motion. So if you are successful in finding such axis about which the body performs the pure rotation, and this point need not to be inside the body, it could be outside the body, then such axis we call instantaneous axis of rotation. And it's a really powerful concept. And why it is powerful? Because about that axis the body performs pure rotation. So by uniquely defining the omega, I can analyze the motion of any point A, B, or C, or any for that matter, any point. So the beauty of pure rotation is that the motion can be expressed in terms of angular quantities, and we need not to worry about the translatory motion at all, because every point is moving in a circle of some radius, one radius or the other radius, and every particle will have same omega and same angular acceleration alpha. Therefore, the analysis of motion becomes fairly simple, and we totally ignore the translatory behavior and we only stick to the rotatory behavior to analyze the motion. So that fundamental benefit will be there with us, and that is why it is very important in this chapter to look for such axes. Now, body, every point of the body is one such axis for sure, but in some situation you need to look beyond the body where you can find something about which the body performs pure rotatory motion. So now the whole idea of pure rotatory motion is to prevent the translatory description of motion. Now, like we can just deal with the angular kinematics or angular dynamics, and we are done with the problem. So we need not to go back to the center of mass, what it is doing, what it is not doing. I need not to bother about the translation part. So that is the benefit we are looking for, and that is the sole intention in defining such motion. So pure rotation is something which we always look for. Okay. So this is the whole idea.
Certain accept that axis, other axis will give
Pardon?
certain accept that axis, instantaneous axis, the other axis would not give the pure rotation.
Correct, correct. So if we have any other axis which is neither part of the body and nor IAOR, instantaneous axis of rotation, then in those axes or in those frame, the motion will be pretty complex, and it's good to avoid such frame. Because the whole idea is to simplify the analysis, and if you're trying to make it complicated by some means, then that is not like accepted. So we need to look for something which is simple, mathematically simple, not just simple, mathematically simple, and which can be analyzed in one particular uh, you can say thinking. Like I need not to go back to the translation, I can just analyze thing in terms of rotational dynamics. So every problem of this particular chapter can be solved by two ways. Either you solve by the layman method, in which you have to write translation separately, rotation separately, and then combine both. And one is the other, the smarter way, which is called the IAOR method. The IAOR method, which is for the instantaneous axis of rotation, is a method in which we get the answer in one line without you know, putting any effort. So it's so fast, it's so efficient that even the question of IE reserve you can solve in fraction of seconds. It is so powerful method. So I'll show you that 99% question we can solve in one line. Most of the rotational motion question you can do it mentally or in one line without solving anything. And if you look at the general solution in the given in various books, you might see somewhere it will be like something like half page long, maybe sometimes it goes 1 page long. And trust me, we can do it in one line. Now, to do in one line, we need to actually understand the basic, like what we are going to do in this chapter. So, in this chapter, our intention is to look for one intelligent axis called the IAOR. And in the frame of that axis, the motion becomes pure rotational. And the moment the motion is pure rotational, we say that the degree of freedom is only rotatory degree or rotational degree freedom. So we avoid the translational degree freedom in that frame. Okay, and then we solve by the one single formula. So that is what we learned in detail. And what we are going to learn, in the next few lecture will be the constraint equation. Like if a body is subjected to some constraint that you cannot move this way or that way, let's say, for example, when you walk on a surface, there is a constraint. And what is the constraint?
You
Your
cannot
foot
go
will not,
down.
you cannot go down. That's the one constraint, that's correct. And that is your foot cannot slip backward. Then only you move, right? So you know that
Yes.
the friction will stop your foot from going backward, and then you just put yourself forward and you walk ahead. So the entire idea of constraint in case of body is very important, because unless we do not know the constraint that the body is supposed to move this way only, we cannot write certain relationship. And unless you will not write the relationship between the velocity and angular velocity, acceleration, angular acceleration, then it is really difficult to solve the question. So before we actually solve the laws of motion question of this chapter, we need to understand the constraint relation. So the next few lecture will be constraint, and the constraint lessons are pretty easy. A part of it I have discussed in circular motion, but again I will just recap for many who have joined recently and not aware of how to do the constraint. Will do the constraint part. But anyway, if you have not watched the circular motion video, do watch it, and the rest will see in the next lecture.
Okay, sir.
Bye.
Nice.